Hi, let's take a look at this reaction. In this video, we're going to talk about reaction quotient, represented as QC or QP. And if you take a look at this reaction, the equilibrium constant is already given to us, which is a pretty big number. That's 5.6 times 10 to the power 5. It's a pretty large number. And what this equilibrium constant means is that there is a certain concentration of NH3 and a certain concentration of N2 and H2 present at the same time at equilibrium. Now, what this means is that there is a forward reaction taking place and a reverse reaction taking place. The forward reaction is producing the NH3 and the reverse reaction is producing the N2 and the H2, and the rate of production of NH3 and the rate of production of H2 and N2 are at the point, they're at a dynamic equilibrium, which means that the NH3 is being produced and consumed at the same rate, which means the effective concentration is going to be constant. Same story for H2, same story for N2. Therefore, the equilibrium constant is a particular number at 25 degrees Celsius. Now, what happens if we start the reaction and we do not wait for equilibrium? If we start this reaction and do not wait for equilibrium, then what's going to happen is your reactants are going to be a lot. There's going to be a lot of them present at the beginning, and then they're going to slowly start being consumed over time to form the product. And as they start being consumed over time to form the product, these reactants are going to deplete while the NH3 is going to increase. Okay? And if we had to determine what is the value of the equilibrium constant before these quantities became constant, then we would get something which we call the reaction quotient, which is represented by Q. Q is basically telling you what is, if we had to try to determine where the reaction is with respect to equilibrium at any point in time, we can use the same expression. So if I take QC out here and I try to, if I assume that's K, we can use the same expression to determine the reaction quotient as we do for reaction equilibrium. Okay, so QC would be NH3, concentration of NH3 raised to the power of 2 over the concentration of N2 times the concentration of H2 raised to the power of 3. Now, because this is not at equilibrium, what we'll notice for QC, depending upon where we are at with respect to time, if it is at the very beginning of the reaction, then you're going to have many more reactants than products. Therefore, this value of QC is going to be much less than the value of K. Let's call that KC. So the value of QC is going to be much less than KC because we're going to have too many reactants. So there's more reactants than you would expect. But as the reaction proceeds towards equilibrium, the reactants are going to deplete. So when equilibrium is reached, then the amount of reactants is going to be the exact same number you would have for the equilibrium constant. Therefore, at QC, when QC is equal to KC, then you are at equilibrium. Now, what happens when if you have too few reactants and a lot more product than at equilibrium, then you've passed the point of equilibrium. Okay, if you've passed the point of equilibrium, then because the products are much higher than the reactants, this number becomes much greater than Kc. Therefore, Qc is greater than Kc. So therefore, you have passed equilibrium. And in this particular case, I forgot to mention, you have not reached equilibrium yet. So what does this mean? This means that if the value of QC, so let's take a value off the top of my head, okay? So let's go ahead and I'm going to erase this expression because it's the same. Let's go ahead and assume that the value of QC is 1.2 times 10 to the power 3. Clearly that value is much less than that value, right? Therefore, it means that QC has yet to reach equilibrium, therefore the reaction will move to the right. Okay, so therefore the prediction out here, I'll create another column. The prediction will be that the reaction moves towards the right, which means more products will form. More products will form. Now, what if QC is equal to KC? Then it's the same value as KC, 5.6 times 10 to the power 5. Then nothing's going to happen. So that's the case of no change, right? No change, no net change, because the reaction is at equilibrium. But what if QC is greater than KC? Then let's say your number ends up being 7.5 times 10 to the power 6. Well, that is much bigger than this number. Therefore, turns out in this case, the reaction is said to move to the left, which means more reactants will form. Now, another way this can be represented, okay, so notice carefully, I wrote QC out here, QP. So if you measure concentrations in terms of partial pressures, then you're going to, let's say this was KP, then you would compare the value of QP with KP, which is essentially the same thing in terms of partial pressures. So just so we're very clear, QP would be the partial pressure of NH3 raised to the coefficient 2 over the partial pressure of nitrogen raised to the coefficient of 1 times the partial pressure of hydrogen raised to the coefficient of 3. There you go. I hope that's not too busy. I hope that makes sense.